Today we're going to talk about two questions, but I'm going to submit it into two different videos. So this is the first one, the question 26, the Sonny Boy problem. And in the submarine location problems, it is often necessary to find a submarine's closest point to approach to a sonobuoy in the water. Suppose that the submarine travels in a parabolic path y equals x squared, which is shown down here, and the buoy is located at the point 2, -half. So the first question is, how is the value of x that minimizes the distance between the submarine and the buoy is a solution of the equation of x equals 1 over x squared plus 1. And clearly this is an optimization sort of problem, and what we are trying to optimize is the distance between the submarine and the sonobuoy. So we need to have an equation of the distance between the submarine and the point. So here we go. So the point of the submarine is considered as x squared, and the point is 2 -half. So we can write the expression of the distance as the square root of x minus 2 squared plus x squared plus half squared. And remember, if we want to try to find the shortest distance, we have to take the derivative and find a critical point so that we can determine whether there's a, so we can know where at which x-intercept there is a local maximum or local minimum or something, well, some other things. So we need to take derivative. Y prime equals to half of the x minus 2 squared plus x squared plus half squared, and also times the derivative of the inside, which is 2 times x minus 2 plus 2 times 2x, which is the derivative of the inside, and times x squared plus half itself. Now, if we want to optimize, we need to find when the derivative of y is equal to 0. And in this case, we can easily tell that this part will never be 0, and we don't want a 0 in the denominator. We want a 0 in the numerator right here. So this turns out into 2 times x minus 2 plus 4x times x squared plus half equals 0, and which can be written as, well, I just keep the process. I'll do it one by one. Minus 2x minus 4 plus 4x to the cube plus 2x equals 0, which can be simplified as x to the cube plus x minus 1 equal to 0. And this doesn't look exactly as the thing we want. We can look at the question itself. It is x equals 1 over x squared plus 1. But if we just make some changes to this equation, like so first we put this to the right side, which is turns out to be x to the cube plus x equals 1, and the left side is equal to x times x squared plus 1, and then we can write it in the form of x equals 1 over x squared plus 1. And this is everything for question A. Now take a look at question B. Question B says to solve the equation with Newton's method. And as we can see, this if we want to use this equation to write it into, if we want to take the y as, well, let's say x squared plus 1 minus x, then it would be pretty tricky and annoying because you're going to take the derivative, and the derivative involves a quotient rule, which is, well, pretty not clean. So we want to use the original form. We want to use the y as this one. So let's say y equals x to the cube plus x minus 1. And the derivative, which is much easier to write, which is 3 times x squared plus 1. And according to the graph here, well, this is a nicely drawn graph in the textbook, and we can estimate that the point is between 0 and 1. So we can start our estimation from through x0 equals 1, and we take x1 equals 1 minus 1 plus 1 minus 1, and over the derivative, which is 3 plus 1, which turns out to be 3 over 4. Well, this is getting closer, and we're going to keep doing that for a while. And it is 3 over 4 minus 3 times 3 over 4 squared plus 1 over 3 over 4 to the cube plus 3 over 4 minus 1, which is, well, I just skip the calculation part because I have already done that before, and the answer is 3 over 4 minus 11 over 172, which is approximately 0.6860. Well, this is getting more precise, and if we do that again, if we try to approach an x3, and well, we just skip it again, and we can get an answer of 0.682334. Well, this is very, very close. This is, well, almost the exact result we are looking for, because when we are looking for x to the cube plus x minus 1 equal to 0, we're looking for its roots. And when I put it in my calculator and it shows a graph, it only has one real root and two complex roots. So the graph turns out to be like this, or well, this is terribly drawn, and this point is 0.686233 blah blah blah. So it's done. This result we have done through using Newton's method is very close to the exact value we're looking for.